Hey guys, today we got something quite exciting. We have this new Twitter thread by Alex Young about his company. It's offering embryo selection, and they've just published the Twitter thread summary as well as a white paper and a blog post summarizing the white paper plus some additional stuff, as well as an embryo simulator. So I've just finished writing a summary of this, which you should definitely check out. And of course, if you're a nerd, you should also read the technical paper and the blog post. But supposing you don't have time, you can listen to this video instead. So embryo selection involves a few steps, and the most important thing is that because you're choosing among genetic siblings, you need to take special care in the methods. And there are two reasons for this, two main reasons. First off, the validity of some polygenic scores declines within families. It declines for various reasons, overfitting to family variables or whatever reason, exactly indirect effects, genetic nurture, this sort of thing is currently all the rage. But another important reason is just that among siblings, there is obviously half the genetic variation that there is between unrelated people from the same population. And so any genetic predictor will work somewhat worse because you obviously cannot make as great genetic predictions if there's less variation to work with. So that's the fundamental limitation. So to deal with this, they've conducted comprehensive validation studies using both unrelated and siblings. Mainly these come from the UK Biobank, or maybe entirely. In the UK Biobank, because it's so large, 500,000 people, there are a lot of siblings and some parent and children, which you could use, at least if you want to deal with age controls, or more extensive age controls, shall we say. And after doing their model results, comparing the between to the within families, they also compare these to the competitors. And so, first off, we can start by looking at the validities here, and they've converted things to the liability R squared. What it means is that R squared has a certain definition when you're dealing with continuous data, right? Continuous data being a value that can, in theory, go anywhere from minus infinity to positive infinity. And you can calculate the accuracy of a given model by saying there's a predicted value based on genetics for something, say height. The real person is 180, you predicted 175. The difference is 5. You square these and you can sum this up and convert this to the R squared. And essentially these two variances, the ratio of these. With binary traits, it's not so easy, so you have to use some tricks to make it sort of on the same scale. One of these is the liability one. There's a few other ones, but they've chosen this one, probably common in genomics. So what we see is that there's a variation among how well certain traits can be predicted. We see the prostate cancer and type 2 diabetes. There's relatively decent models for this. They have achieved roughly 20% variance, whereas for like melanoma or testicular cancer, the abilities are less impressive. The differences then they compare to the sibling comparison to the population one, and you can get the ratio of the betas, and that's what you want. Because of course the variance among siblings will also be smaller, so the R squared value among sibling pairs is not directly comparable, and it's not really kind of what you want. You want to know the differences in this betas. If the model predicts with a certain beta used in, like, say, logistic regression, then this value should be the same within siblings. That would mean that there's no overfitting between families and stuff. And these betas are, importantly, they're not related to the reduced variance. So they're on the same scale, unlike the R squared values. So across their medical traits, we basically see there is no difference. There is one here for osteoporosis, but you can see the confidence intervals are very close. And so considering that they did 10, 15 tests here with no control for multiple testing, this one is probably a false positive or a negative, as it is here on the negative side. So essentially for diseases, as academics have also found, there's not much decline within families for these models. They're not overfitting to some social parameters or hidden population structure that somehow does something. Of course, also there's differences in the validity as we see here, right? And we can of course wonder why is this? Well, there's roughly three factors in this. First is the sample size. For some of these, there's just more data available, more data, for instance, because the disease is more prevalent or it's easier to measure. So prostate cancer is, I think, the largest killing cancer among men, if it's not lung cancer. And type 2 diabetes is much more common than certain other things. Testicular cancer is kind of rare. So just the prevalence means that you will have like less cases in your data set. And since these are usually coded binary, you want a lot of cases, right? But if you can only get like 300 in the entire UK biobank with 400,000 controls, this can be a problem, right? Second, there's the inherent difficulty related to the genetic architecture of this trait. And so this essentially has to do with the degree of polygenicity. So how many variants are explained, or how many variants are involved in explaining a particular trait. And of course, if there are a lot of variants, and then of course on average they will have relatively small effect sizes, and then trying to estimate these precisely to build an optimal prediction engine is much more difficult than if you're just looking for like 10 variants in common that vary a lot between people. And furthermore, you have, if there are non-additive or interaction effects, genes that have a certain effect when they are together with a different another variant, but a different effect when it's together with another variant, right? Then you need more statistical power to find and estimate these interactions, and you may not even know they exist. So you would also have not only to try to estimate them, but also find them in the first place. Due to the extreme number of variants in the human genome, 3 billion base pairs, okay, only maybe 100 million of these vary between humans, and maybe 10 million are sort of common. There's like, if you look at all the interactions, right, it's 10 million times 10 million divided by 2, which is certainly a too large number that you could plausibly test for, at least with the current sample sizes. There are some tricks to make this smaller, but nevertheless, it's like a daunting combinatorial explosion. And finally, of course, you cannot build a genetic model that predicts a phenotype or a trait of some sort if it's not heritable, right? If genetic variation is just not important in what causes a particular disease, if it's due to some environment thing that is not controlled by your own behavior, but some government or poison in some local lake or something like this, air quality, something you can't really influence much, or on average you don't. Then of course or it could also be just kind of random, like many cancers are. In that case, if it's not heritable, you cannot build a good genetic model to predict it. That makes sense. So these three factors come together to explain why it is we see this variation in the heritability across these traits. And very interesting is that they also provide an embryo screening tool. So if we go to their website, you could play together with this. Here we're looking at intelligence. We could pick, prostate cancer. We could say like one father with this. My mother could not have it, you could say I have 10 embryos, I have 20, I have only 5. You can play around with it how you want. Maybe my mother is Chinese, so we have to pick East Asian here. We'll see how this is important later. Whoops. So here I've looked up a kind of typical case, just to give an idea of what 20% liability means, right? The heritability of type 2 diabetes is something like 70-80%. So it's mostly due to genetics, but that of course does not mean that we can find all the signal yet. And so in this case, I've chosen 2 European parents. In the left case, we have no one in your family has it, but the average risk in society is about 15%, and you have a kind of normal number of embryos, 10, which would typically be the case for someone in their 30s who extract embryos, and if they're not super lucky, they might get 15x or 13x, and these will then convert into 10 embryos that don't have the wrong numbers of chromosomes, like Down syndrome and other things that are non-viable. So in this particular case, what we can see is that if we were to try to pick the worst embryo, that on average would have about 30% chance of having type 2 diabetes at some point later in life. This assumes current trends about the prevalence. If treatment becomes better, as with the Ozempic stuff, we may be less interested in diabetes if we think it's more treatable in the future. And the best embryo has only 5%. So you can see if we look at the ratio of these 5 to about 30, it's about 6 times improvement between the worst and the best on average in a batch of 10 embryos. So this is quite a large improvement. We can also think of the situation where you have extensive family risk. Both your parents have type 2 diabetes, in which case the chance that that is to say you yourself and your spouse have it, if this is the case, then your child has a 45-ish% chance, again using the current trends assumption, which for the worst embryo becomes 66 and for the worst 25, or the best 25. So here the ratio between these numbers is smaller, 2.6 or so. So in ratio scale, you will get less bang for the buck choosing the lowest risk one here, but in absolute risk chance or scores percentage, which is the one you should care about in real life, especially if you have family history for something. That's especially when something selection like this is very beneficial, because you can get the improvement here is almost 40% points decrease in your child having type 2 diabetes, again, with current assumptions about trends and stuff, which is like a massive improvement compared to over here where the difference is about 20, what you would get 2025. So especially if you have something bad in your family, something that is due to like polygenic stuff, then this is like very beneficial. And I know there are a lot of IQ nerds watching this stuff. Welcome. And so we can also, of course, look at how many gains can we save civilization? And the answer is yes. So first we got to deal with some stuff. I've run surveys of my readers, and the average IQ according to SATs and people who report their scores on certain online tests, it seems to be about 130. If we take the spouse correlation, is about a half. So that would mean on average, if someone is reading my blog, their spouse on average would be half as far away from the mean in IQ. So if 130, then the spouse will be 115. The average of these two is 123. Then what we really want is the family mean IQ from the genotypic one. It doesn't say genotypic, but if you use the mouse over, it says it. Whoops, we have to use intelligence. The mean genotypic of the parents, right? So that's the most important thing, because there will be some regression towards the mean, because one of the reasons that a given person deviates so much from the average IQ or height or any other trait is just that they were lucky. It wasn't all due to genetics, or if it was due to genetics, it wasn't additive genetics. So what you want to know is the additive heritability. If we assume this is, say, 70% most of the heritability, the total heritability, this would mean that the mean parental IQ genotypic one is about 115. So that's the average IQ of your child. If you have two 130 IQ or parents whose average IQ is 123. The index parent is 130. If you do this, then this is roughly the results you will get with their predictor and these assumptions. So you are looking at a roughly 7-point gain from 10 embryos. So that's non-trivial, but considering the parents are 123 on average, using this service will give you to 122. So on average, the child will still be lower IQ, even if you pick the highest embryo of 10 on average. And the reason for this is the regression towards the mean. We can only move the genotypic mean up a little bit every generation. And because you cannot directly select on the genotypic mean when you select, you can, of course, with this, but using embryo selection. But in general, nature selects on the phenotype, not this. And so you get this regression towards the mean. It doesn't mean, as many people think, that you can never go away from the mean. Like, this would mean that evolution is impossible. Traits can never change. If like some people start breeding for intelligence, then they will all just go back down to hundreds. Many people make this mistake, but that's because they forget that in every generation where you select for something, the new mean genotypic IQ or height or whatever will change upwards or downwards depending on direction. And so it just means that the response to selection is slower than what you seem to be getting, which is in fact a different way to estimate heritability, as you can select pigs, let's say, for amount of pork you can get out of them, And if you keep selecting the, say, the top 10% picks for porkability, we could say, what you'll find is that they improve at a certain rate that is lower than what you see, but than what you're getting based on the phenotype. And the ratio of these two will also give you the heritability, the realized heritability. That you will find this often if you read animal breeding studies. So given that the typical IQ decline for a Western country is maybe maybe 2 points per generation, a 7-point gain from this current technology is quite enough to offset this. But that, of course, assumes that everybody's using it. If you could calculate which proportion of the population would need to use the service to prevent an overall decline in the population IQ, and that would be some ratio of these 10-15% or so, maybe 20. Anyway, so that's essentially, it is possible with current technology using this to offset it, and you will give your children a better risk or a better chance in life for whatever high occupations and all the other good stuff that comes with IQ, as well as you can, of course, minimize the chance of diabetes and any of these other things that you might care about. Breast cancer, for instance, is quite common. So that's quite nice. The other thing that was important we saw that you could pick non-European ancestry in the simulator. And so why does this matter? Well, it matters because when you train a genetic model, what you're really just looking at is you're looking at some variants in the genome. Someone has a T or 2 Ts, someone has a G or 1 T or 2 Gs. Right? And you do this across, all the variants you've included in your study, which is typically about 10 million. These are the relatively common SNPs that you can measure using microarrays or imputed microarrays. And so in general, what you would want to do for your optimal model is you would find the causal variants, and then you would estimate their effect sizes, and then you would add them up in your genetic prediction model, and this would work across ancestries. Mostly. There's also some frequency dependent issues, but frequency stuff aside, in general, your model cannot figure out which of many variants in the genome is the causal one. And that's just because there are so many of them, so many variants. If you find, let's say, one gene or protein region, it codes for some protein that does something in the brain, maybe having a slightly more efficient pathway gives you 1 IQ or 2 IQs or whatever. And so you'll find in this pathway, there may be, 5 genetic different variations that slightly alter the efficiency of this pathway, but there will not be 5 SNPs that associate with these, because variants that are close to each other on the chromosome are very highly correlated because they get inherited together in these big blocks during the recombination. And so it means that when the model is trying to figure out which of these variants is the one doing stuff, it can't. Because you have so many variants that are so highly correlated when they're right next to each other, the model simply cannot figure out which one is the causal one. And so on average, it will not find the causal one. It will find a non-causal variant that has a high correlation with the causal one, so-called tag SNP or tag variant. And when you find tag variants instead of causal ones, then because you're relying on the proxy, you're relying on the strength of this correlation to get the validity out from the causal one. And the reason this declines is that different populations, due to different population history, don't have the same correlations among these variants, right? They arise from random recombination and stuff, and how common certain these haplotypes are in the haploblocks. Which one is it? Whenever these blocks of variants in a place in the genome, and so the more distant your training population, in this case, since most people use UK Biobank, it's mostly British white people plus some American whites and this sort of thing. The more distant you are from essentially these North Europeans, the worse the predictor will work on you, to the degree that it is based on tag variants. And so this really leads to this predictable decline that you see here, where the more distant populations from British white people, Nigerians, Caribbeans, which are some mixed Africans, Chinese, Indians, and so on, they have worse validities. And also the populations that are very close, Poles are very close, right? They're Slavs, but Slavic people and Germanic people and the Romance people that eventually inhabited the UK, the British Isles. These are very closely related populations. They only split a few thousand years ago, whereas the split with Nigerians was 100,000 years ago or whatever, since out of Africa times, and somewhere intermediate for Indians and China. And there will be some somewhat better overlap with Indians because of the Indo-European overlap, even though it's relatively small in Indians and mostly North Indians. So for this reason, you will get a decline in the validity of the models, and this will then be something you have to take into account, because when you're giving people a chance of some disease, you're saying on average you have 2.6% chance of melanomas, but if you're like, I don't know, African, then it's smaller, right? And so the model, whether you're gonna act on this information, depends on these absolute probability values. But since the absolute probability values and the kind of the difference between them, the ratio between the highest and the lowest and the highest, this one depends also on your ancestry and will be slightly worse if you are of not North European ancestry, especially if you're African. So that's just inherent to this method, that until large African biobanks are collected, probably has to be done in like the US or Brazil or countries with large amounts of Africans and enough money to do this kind of biobank. Until these are included in the training samples, until this happens and the models are then taken into account and finding the more causal variants, or at least better proxies that work across ancestries or races if you want, until then the genetic models will continue working better for Europeans who contribute roughly 75% of the genetic data in the databases. Finally, they compared their model results to those of the academics. So here they have two studies, Thompson et al. And Mars et al., as I recall. And we can see that for many cases, prostate cancer, Heresight does some additional fine-tuning of the models, try to really squeeze out extra validity using bioinformed stuff. So you look at, if you find a bunch of SNPs, all of which predict, say, prostate cancer, and you don't know which one to pick. Now, normally you would just use the one with the smallest p-value, and you pick that one as the leading variant or the top variant. But you can do also biologically informed stuff. So you find the variants in this kind of in this area on this protein, typically inside a protein. You look at what kind of variant it is. Is it synonymous? Some variants, if you have a T or an A in some position, it will code the same amino acid, so it's a synonymous variant. So it's not likely to do anything causal. There are a very small number of known cases where this is somehow the case due to weird biology stuff. But in general, if it's a synonymous, then it's not likely to be causal. In the same way, you can look at how often certain areas of the genome are read, so the expression and certain other tricks that you can essentially use to figure out which ones of these variants around some protein are the one that is most likely to be causal. And using this information, you can slightly improve the model and how much it generalizes across ancestry groups. And so comparing Heresight's optimized models, you can see that they beat the competition in most cases. There's a few exceptions, glaucoma here. But mostly they're in line with the competition. They're slightly better on average, and less, more so for the Mars paper. But the Thompson one is quite close. So this shows that the results they're getting are sensible, right? They're not too far from existing academic work to be unbelievable, but they're still better. And these come from good model fits and sibling validations and stuff. Comparing to the competitors is a different matter, because here we have what the competitors are claiming or have shown in their white papers or validation studies. We see that Heresight is quite a bit better. Sometimes 2-3 times better in R-squared terms, which you shouldn't use, but nevertheless in these terms. And I think the reason for this, if you check the papers by these people, often they don't do their own fine-tuning at the end. They use outdated models, so they're not really offering their clients the best thing they could be getting with the current technology. And so it's unsurprising that Heresight is offering this, given that they have researchers who basically do nothing else about this topic. You can read their the research published by the various members of the Heresight team. They're on the white paper, so you can look them up on Google Scholar. Anyway, there's one competitor that's not listed here. We have Heresight, Genomic Prediction, and ORCID. These are like these are the established players. Genomic Prediction was the first, ORCID, I think was the third, and there was a second one which no longer exists. I forgot what it's called, or maybe it's doing something else. So one of them is missing here. It's Nucleus embryo. That's the one that just a few weeks or maybe a month ago made splashes, and they're now offering, selection. You can select for anything you want, IQ included. And so what you can do is that you can read their materials insofar as I have any, but you can also get, if you somehow know, you can get some people to sign up to be customers, and they can give you results for your embryos for Nucleus. And what you'll find when you read their reports is that some of the values are unbelievable, because essentially, for instance, for some traits or phenotypes, diseases, they give you like predictions that for risk for an embryo that have like very large differences. So what it means is that they're indirectly claiming to have a good model, right? If you have a useless model, the risk for the worst embryo and for the best embryo will be the same risk if the model has no validity, right? And so insofar as the upper and the bottom, the best and the worst embryo for a given disease, insofar as these values differ, you can indirectly backwards and estimate how good the model that they have used is, or at least how good they claim. And so what you see here is that they did this for a bunch of the things that Nucleus is claiming, and you can see that Nucleus is claiming predictive models that are much better than anything that exists mostly in the real world. For schizophrenia, it's aligned, but for many of these OCD, they claim a model that essentially has 10% variance liability explained, and that's like the best academic model is not even 1%, so it's like an impossible result. Either they have like super secret source data sets of millions of people that no one else has, or they misspecified things. And you can compare the same thing here, where almost all the errors, right, are in the are below the thing. So they're over claiming, right? These models cannot possibly be this accurate, they're claiming. And you can also look further into this, because Nucleus is just a rebranded version of ImputeMe, the website that used to be where you can go upload your own genome, get some predictions. And these were all based on ImputeMe. They were based on existing GWASs that were up to date at the time in 2019, 20, this sort of thing, when or whenever it was the website went down. And so the source code for these is known, so you can look up and see which exact GWAS was used in ImputeMe for OCD or ADHD or whatever. And so you can compare this to what Nucleus claims in the report, because they also give you information about how many variants are used. And so often you'll find most of the time that it's the same model, the same 5-year-old unoptimized model that they're using, and they're only using often significant SNPs, not using all the SNPs, which is very bad for prediction purposes. So in general, the work just seems to be kind of incompetently done and over-claiming, and they went far too early to market. They should have hired some people who knew what they were doing. That's unfortunate, but that is the case. I mean, of course, Nucleus may have a great reply to this stuff, showing us that indeed they have a secret sauce models that work far better than anyone else. But until that happens, if that happens, then this is the state of the art. And so you can dive in more to this. There's some more stuff. For instance, some values they reported were impossible. For instance, in one case, an embryo was claimed to be of a slightly above average polygenic score, say 0.1 or so, but the probability for the same embryo is listed as below average. These two values are impossible together, right? So in general, it seems dubious, and since they've only been out about 1 month, probably not too many people have gotten this product yet, or have bought their product yet. In any case, of course, I think this covered roughly what this here. They also have this this nice explainer one that covers a lot of the same stuff I covered here, and as well as some other things. And if you're a bit nerdy, you can read their 40 paper preprint, which has a lot of details for those who are interested in the technical matters. So that's it. I hope you enjoyed this video, and we'll see you soon.